Now let's go ahead and move on to the spread, the standard deviation or standard error. Which one are we going to use? Well, it would be tempting to use standard error that we use for confidence intervals, where we just said, oh, do the sample, P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Um, but the thing is, when we're doing a hypothesis test for P, we actually have a hypothesized value, all right, and for the parameter. So we actually calculated a standard deviation for the population instead of a standard error for a sample. Now, we are going to use our sample to come up with our hypothesized value. We will do that, but we're going to say that's supposed to be the true value, what we're assuming. So in theory, both of our proportions are the same, so we're going to pool them together. We're going to put the greens from my first sample together with the greens from my second, and we're going to call this p hat. And so here you can see I put together my successes on both samples, divided by now the total sample size as if I was putting them together. X1 is the number of successes, for the first sample, and X2 is the number of successes for the second one. The sample sizes for both samples are N1 and N2. Okay, so let's go ahead and revisit my example. We're going to calculate the hypothetical proportion of green candies. So again, I'm starting with this formula. I add 36 and 16, 200 plus 100, and I get 0.173, which kind of makes sense because the first bag has 18% green M&Ms and the second bag has 16%. So it should be close to 17%, but it's a little off because I actually have more green M&Ms, more M&Ms in this sample than this one. All right, so now that we know the hypothetical proportion, we can calculate the standard deviation using only p hat, not P1 or P2. Now we still have to treat the two samples separately, so we're going to have a formula very similar to what we used for the confidence intervals, basically with the two n values. The main differences are that it's for standard deviation instead of standard error, which I've signified by going sigma p hat, and p hat replaces both P1 and P2. So if I put them in there, looks a lot like our other one, but remember you're putting a pooled proportion in here. Okay, so let's go ahead and calculate the hypothetical standard deviation. Remember my p hat was 0.173, so the only thing different in both of these is the sample size. Simplifying, I get 0.0463 for my standard deviation. Okay, so the next step, the do step, is the same. We're going to calculate a z-score and a p-value. So first of all, I need my point estimate, which is the difference in my two proportions. I have 0.18 minus 0.16, and that's 0.02. So I'm going to use that to calculate my z-score. I'm not doing the average of the proportions, and I'm not doing p hat. I'm doing the difference, because remember, we're comparing the difference to 0. And in fact, there it is. We're comparing the difference to 0. Here's my new standard deviation, which I have here. And if I go ahead and divide that out, I get 0.432. And one thing you need to remember when you're doing this, it's really helpful to go ahead and draw the standard, the normal distribution. Mark where your z is, which is roughly about there. And which way am I shading? I'm assuming my alternate hypothesis is that P1 is greater, P2 is lower, so this difference should be greater than 0. So I'm shading to the right, which helps me determine how to calculate my p-value. I'm going to do normal CDF from 0.432 to infinity. On your calculator, that would be 1,000, all right? And I get 0.33. And the conclude step is the same as well. So with a p-value of 0.333, which is greater than alpha, we fail to reject the null hypothesis that the proportion of green M&Ms in both bags are the same. There is insufficient evidence that the true proportion of M&Ms in the second bag is less than those in the first bag.